Is it red on yours there, James?
It's on mine. It says Marion's recording the call.
Okay, all right.
Yes, sir. Red as well.
Okay, I've got mine set up to different colors with all I got. Okay. Our 47th lesson. I realize we're dragging this out, but I'm trying to be very thorough in it because there's so much arguments against the flood, and we need to answer them and give a good background for the child of God to be able to defend the faith, defend the truth. So, yeah, errors in modern geology. We introduced this last week in our last lesson. Now we're looking at radiometric datings. We're kind of in the middle of radiometric datings, and we're going to look at radiocarbon dating techniques next. We'll look at some other dating techniques a little bit later in this study. We're looking at the problems with radiometric dating. It's our fourth problem. We actually introduced this a little bit and didn't finish it last week, so going back and picking it up. And we have here the fourth problem with it is the system assumes, and it's really a dangerous thing when you have to have your mathematics based on assumptions, your arguments based on pure assumptions. And because you can assume various things, if you wanted to prove something or appear to prove something was true, you could just assume a value and start off with that value and do your math. And you could actually work it backwards, figure it out, and then I call it reverse engineer it. Okay, so you could reverse engineer your math and figure out what you needed to assume about the initial conditions. So the system assumes that the initial value of some radioactive isotopes. Now, isotopes is, let me illustrate this. Hydrogen has an isotope, and what we have is we have isotopes of various elements will have more than one value. It'll have an element will have the same value of protons in the nucleus, but it may have a different value of neutrons. And the different values of neutrons, it'll still, with the same value of protons, it'll still be the same element. So we'll look at carbon a little bit later and some other elements, but they can have different values on them of neutrons, but the same number of protons, and that would make them have be the same element. And so that's an isotope. They're the same element, but they have different number of particles in their nucleus. Now, by particles, I'm talking about neutrons, protons, or a combination of those. So this system assumes that the initial value of some radioactive isotopes of some elements were equal to 0 at time equals 0 at the beginning. They make an assumption about this without any way of knowing it. Now remember, science has to be something that is verifiable by empirical means, by actually using one of your five senses to determine it. Either see it, feel it, smell it, taste it, or touch it. So you use one of your five senses: smell, taste, touch, and seeing and hearing, your five senses. And if we weren't back there at that time, we don't know what these values were. We may make arguments to extrapolate backwards on it, but we have to make assumptions about those extrapolations. Remember, the extrapolations, when they do them, are almost always based upon linear extrapolation. Assumption of no cataclysmic events, nothing happening. And that's uniformitarian geology, assumption. With the decay of iodine-129 into xenon-129, Allegre and Snyder admit that xenon-129 exists at the beginning of the Earth. And so they admit that xenon-129 existed at the beginning of the Earth. And that's a very, very interesting admission. Xenon-129, they say, arose as a result of nucleosynthesis before the Earth and solar system were formed. It was also created with the decay of iodine-129. So Xenon-129 came about, they say, before, and it also came about as a result of decay of iodine, which does not exist on the Earth anymore. So we don't have any iodine-129 anymore. Can't find it, that is. What they mean by that is we haven't found any. This form of iodine was present very early on, but has died since, and Xenon-129 has grown at its expense. So that's their claim. Now, so they say we have a certain amount of Xenon-129, and then they use that to argue how old the Earth is. How does a writer know how much Xenon-129 and existed? Now, the 54 is the number of, that's the way I learned it. It was 54 is the number of protons, and 129 is the number of total particles. That would be the protons plus neutrons in the nucleus. How do they know how much exists at the beginning? They have to make an assumption about how much existed, and that's an assumption they have to make. How does he know that all the Xenon-129 in the mantle of the Earth decayed from iodine-129? How do they know that it decayed from it? They don't have any way of knowing. Now, if you look at this, they have to make an assumption. These assumptions are nothing but assertions about it, are nothing more than pure assumptions. And you can make any assumption you want and get a different age for the Earth. So they have to start out with an assumed value. They start out with an assumed age and work backwards. There's no other way they can do it. And so what we have here is, it's just completely ludicrous. You can't prove anything by it. Fifth, a number of other isotopes are known to exist naturally without being radiogenic. Now, genesis is Greek for the beginning. So what they're saying is radiogenic is that it originated from radioactive decay. That's what that means. However, some strontium-87 exists naturally, not as a result of rubidium-87 decay. So now then we get over here and say, well, we've got strontium-87, and how did it get here? Well, it came as rubidium-87 decay. Well, if that's true, then how much strontium-87 did we have to start off with? None, or some, or how much? Because if we measure the amount of strontium-87 and take the rate of decay of rubidium-87 into strontium-87 and use that to calculate the age, we got to know how much strontium-87 we had to start off with that wasn't manufactured or created by the radioactive decay. Again, they don't know. And again, it's not science to begin with. Why? It's not science because what they get in is they are not back in time to look at what happened there. It's all based upon their assumptions. What complicates things for the uranium-lead method, and same thing happens, uranium decaying into lead, is that non-radioactive lead 204, 206, 207, 208 also exists naturally. So we use uranium and figure out, okay, how much lead there is, lead 204, 206, 207, 208. Look at them and say, okay, we can use that now to figure out how long the Earth's been here. Because we've taken all this, they have to assume that the amount of 204, 206, 207, and 208 lead started out with some value. And how do they know how much they had to begin with? Notice they admit here, Driscoll admits here, they have to say what complicates things for the uranium-lead method, that's the dating, but uranium decay, is that these isotopes, lead 204, lead 206, lead 207, lead 208, Pb is the lead, also exists naturally. And scientists not sure what ratios are non-radiogenic. that is, didn't originate from radioactive decay to radiogenic, originated from radioactive decay later on early in the moon's history. They look at the moon. Same thing happens with the Earth. Got the same problem. The whole system has complications that these isotopes existed in non-radioactive form. They're created, they were there. So we can't measure how much lead-204 there is and figure out how old the Earth is, because we don't know how much lead-204 there was when the Earth was created. And you can assume, if you want a particular age, you can assume an amount that was there and then backtrack with your formula and work it backwards. And again, I call it reverse engineering. If these non-radiogenic isotopes of lead exist on the moon, how can one say it didn't exist on the Earth? That's ludicrous. They did. The isochrone method of dating is based upon this assumption. And so we have a serious problem. The isochrone method is based upon the assumption that meteorites, for example, have the same ratio of isotopes of lead as the Earth. Lead-206, lead-207 as the Earth. How do we know that's the case? How do we know that these meteorites didn't come from somewhere else in the universe or in our solar system that had a different ratio of these isotopes? They don't have any way of knowing it. Again, this is all smoke and mirrors. Isochrone method, according to Brush, here's what he says about this, is self-checking in the sense that if a group of rocks selected does not yield a straight line plot, then one knows that they were not formed at the same time and can reject them. So they have to start off and make an assumption. It's supposedly self-checking. So that's not formed at the same time and can reject them. So that's the assumption, see? How do they know that? They make an assumption. They should have been at a ratio with a straight line plot. Atheists reject meteorites that have ratios that do not conform with the assumed age of the universe, is what he's saying. We know the age of the universe, so we make a plot of these based upon the ratios of which these are formed. And again, they then made the assumptions that there was no variation in the decay rates of these things over time. And that other factors, like such as pressure, heat, and so forth, didn't change them. We had that in our last lesson. The sixth problem with radiometric dating by radioactive metric is from metron, the Greek word measure. Radiometric dating is that they assume that some of the daughter isotopes did not exist at the beginning of the universe and that others did. Now, a daughter isotope is one that's generated by radioactive decay from another element, or from that same element has a different isotope. If large amounts of any of the daughter isotopes existed naturally, we've already shown that several of them, they admit, did exist naturally. The whole system is flawed and cannot be used. It's a flawed system. Since Xenon 129, a daughter isotope existed, how can one say that thorium 234 did not exist at the beginning of the universe? And if it did, how much existed? It's one of the key elements used in their dating methods. This system of dating demands that this assumption be true, but they cannot prove it. And again, it's not scientific to begin with, because it's not based upon empirical methods. You cannot go back and observe it and verify it. You can't go back in time a billion years back and observe this. You have to make assumptions about it and then extrapolate it backwards. Seventh problem with it is most of the radiometric dating of rocks is done on igneous rocks and not on sedimentary rocks. Igneous rocks or rocks formed by solidification of magma, molten that is. Dot and Prothero state because most datable minerals containing radioactive elements originated in igneous rocks, the bulk of isotopic dating has been confined to such rocks. That's true. So this poses a problem. We can't date the sedimentary rocks from it. Absolute age determinations of points on a geologic timescale based on radioactivity are generally accepted as the best approximations now known, even though they rest on a series of assumptions, and one of which may be upset at any time. This is Wells. He admits it. At present, there is no means of confirming or denying the accuracy of the determination by independent methods. We can't prove our assumptions. Yet they will blatantly argue that we've proven it's that old. They haven't proven it. It's based upon assumptions that they cannot prove, and that they have not proven that they cannot prove. Because they don't know how much was at the beginning, how much daughter isotope existed. They can't even say for certain that the decay rates, that they have those right. I found it very interesting when I was studying at various universities. I've taken classes in that if you take just a sample, just a piece of a curve, and try to figure out what the equation for that curve is, you had a problem, particularly if you only sampled a small portion of it. And so that's your problem. When they get into this, if it's 1 billion years and they look at it over a period of 5 years, that's nothing compared to 1 billion. So it's very difficult to actually get the equation for it. The use of radioactive isotopes in geologic dating has many problems. Now, this is another quote. The methods are inexact and contain many sources of error. In order for the system to work, the parent isotope must enter the rock in the absence of any of its daughterite products. And the accumulation of daughter isotopes must be contained in a closed system so that there's no leakage of daughter products out or migration of indistinguishable isotopes into the rock after it's formed. I've already pointed this out. This is a problem. Now, you would argue, say, well, we have this daughter isotope in there, must come from the mother, the source, but the daughter could have migrated in, due to water coming in, bringing it in, or other means coming in through migration through the rocks. It could have come in as a gaseous product and gone upward as it migrated through the rocks. Or as water seeped down through, could have carried it if it's water soluble. There's other ways it could have come in. And so we don't have any way of knowing this because we can't go back and measure and observe everything that happened to it over time. ROP is an atheist. Furthermore, the half-life of the radioactive isotope must be well known. Then he says the last assumption apparently on firm ground, but the others are always subject to problems and errors. He claims the last one, the half-life of the radioactive. This is half-life means if you have 1 pound of radium, for example, in a certain amount of time, half of that pound, a half pound of it will decay into another isotope. That'd be your half-life. Half of it decays. Right, that's what they mean by half-life. The last assumption is apparently on firm ground. He says, well, I've already pointed out that there's evidence that the radioactive decay rate is not so firm and solid as he might think. But the other ones he admits are always subject to problems and errors. But remember, we have 4 variables, we only know 2 of them. Well, no, 3 of them rather. We have to assume one of them to calculate we know 2 of them, and we have to assume the 3rd one to calculate the 4th one. So we have a problem here. And we have to make assumptions about how much originally there was of the of the mother isotope, so from which the other ones come, the daughter isotopes come. This means, he goes ahead, Rob says, that a series of dates run on a single rock may produce quite different results. I admit that. This happens. Of all the methods, probably carbon-14 is the least dependable. Rob admits that we're going to get into carbon-14 dating either tonight or next week, the Lord willing. Now, let's look at radiocarbon dating here as we lead into it. I think we have time to get into it here as we go through this. And we have about 20, 25 minutes. We could probably get into it in some detail. Let's explain it. Scientists assumption about the amount of radiocarbon in the atmosphere. Now we're going to show how radiocarbon is produced and what it is. It's carbon-14. It's an isotope of carbon. And so carbon has 6 protons, and the most stable form of it has 6 neutrons. But we have a carbon-13 and a carbon-14. And carbon-13 has one more. It has 7 neutrons and 6 protons. Carbon-14 has 8 neutrons and 6 protons in the nucleus. That's the difference in them. What they're assuming here is carbon-14 is produced in the atmosphere, and we'll talk about how it's produced in just a moment. And it's produced, they assume that the amount of radiocarbon in the atmosphere is at equilibrium. That means there's a constant value, that the amount that is produced equals the amount that decays. They're stable. But they found out that that's not true, and they admit it's not true. And so that's a serious problem for them. Scientists assume that the rate of decay of radiocarbon is known, and I think that's not true. Third assumption they make on it, assume that nothing has changed, either the amount of radiocarbon, 6 carbon-14, 6 protons, 14 particles in the nucleus. The nucleus would have 6 neutrons, 6 protons and 8 protons, 6 carbon-14 radiocarbon, or non-radioactive isotopes. So there's the amount of the non-radioactive isotopes, 6 carbon-13 or 6 carbon-12, is constant. That's what they're claiming. Nothing has changed the amount of these particles in the atmosphere. Radiocarbon is created by at least 2 separate means. And what we find here is high energy neutron and or proton bombardment from the upper atmosphere. We'll look at this, see how it occurs in a minute. They've also found that lightning produces radiocarbon, and the impact of space objects has been found to produce radiocarbon, interestingly enough, such as comets and meteorites. Now, here's what we have. Cosmic rays, I took this off the internet site, bombard the upper atmosphere. Fast-moving neutrons are produced by the cosmic rays. These neutrons collide with atmospheric nitrogen atoms. And when they do, they form carbon-14, which is a radioactive isotope of carbon. Now, that's what happens. And so the nitrogen atoms are changed into carbon-14. This cosmic radiation then comes in, and this neutron then hits nitrogen-14, which nitrogen-14 has 7 neutrons, 7 protons normal. By neutron capture, it becomes unstable, and it becomes carbon-14. And so here we have one of these neutrons, one of these protons becomes a neutron, and it still has, and it's carbon-14 then. All 3 isotopes of carbon are common carbon-12 and rare carbon-13, and radioactive carbon-14 are absorbed by living organisms. In other words, these organisms absorb this into their bodies. A tree takes it in, as trees take in carbon dioxide and produce O2 or oxygen. that we breathe in. God made it that way, and trees and plants become food for us, but they also help us to breathe. So we have them actually happening. Now, here's what happens. Here's how they date things with it. They assume the amount of carbon-14 in the atmosphere is constant. And we'll see why they make that assumption a little bit later. They make that assumption that it's constant. This carbon-12, carbon-13, and carbon-14, carbon-12 and 13 are stable. Carbon-14 is radioactive. They're all absorbed by plants, grass, trees, and so forth. And some of these plants then die and are buried in the ground. And so now then, they're not taking any more carbon-14 into the wood that's buried, or the stems of the plants. Not taking any more in. Then this radioactive material, carbon-14, begins to decay, and they say they know the rate of the decay. So the carbon-14 emits a beta particle, which is a high energy electron. So one of the neutrons, I just like to think of it this way, it spits out an electron, and then it becomes a proton. And so then it becomes from 6 protons to 7 protons. 6 protons is carbon, 7 protons is nitrogen. And so that's beta decay. So by beta decay, high energy electron, one of the neutrons spits out a proton and spits out an electron and becomes a proton. And that's the easy way to remember it, what happens. And then it becomes nitrogen-14 again, which is stable. Back to nitrogen-14. That's what happens. Now, let's say here that this tree then is buried, some of its stems or branches or whatever, or the trunk of the tree is measured. We can measure the amount of carbon-14 in it, and then this can be done. Now, for a long time their methods of measuring it were very crude, and they've gotten better methods now. But a horse or an animal of some sort, in this case a horse, eats it, takes it into his body, and then his body decays as he dies. So they can measure the amount of carbon-14 in his body. And the theory goes they can measure how long ago that horse died or lived. So we'll be looking at this, but this is how the system works. Are there questions about carbon-14 or radiocarbon dating? Any questions, quick questions right at first? Anything I didn't clarify up to this point? No questions? We'll move on then. Radiocarbon formation starts with a neutron, nitrogen, and it has 7 neutrons and 7 protons in its nucleus. And a neutron comes in, upsets it, and it emits a proton. So a neutron comes in and a proton is emitted. Now, when this happens, it becomes carbon-14. It still has 14 particles in the nucleus, but it lost a proton and gained a neutron. So a proton comes out, that proton picks up an electron, becomes a hydrogen atom. Now then, later, that carbon-14, which is unstable over time, it then emits a high energy electron, and so it's a -1 charge, and the mass is treated as 0. It's not actually 0, but it's very small mass compared to the neutrons and protons. You might think of a neutron as a proton that swallowed up an electron. That's how they used to think of it, but it appears pretty close to that, and gives off some energy here. So this is energy. And so right here, then this turns back into nitrogen. This is your radioactive decay. It goes back to nitrogen again. Any comments or questions about that? We won't go into the chemistry of it. That's not important for us here. Okay. Now, Willard F. Libby made assumptions about the amount of radiocarbon in the atmosphere when he set up the system known as radiocarbon dating. there are 2 neutrons per second per square centimeter coming in, and there are 2. This produces 2 carbon-14 radiocarbon atoms are formed each second per centimeter per square centimeter. That's the rate. So we have this rate occurring. Now notice there's one thing he assumed here. He assumed that this rate is constant. So keep that in mind. He assumed the rate is constant. And that assumption, we're going to see some of the things that we learn about the flood would keep it from being that high. So it would make it appear to be older. All right. Now, the disintegration, he's claiming that there are 2 carbon-14 atoms disintegrating per square centimeter. So he assumed the rate of production, which is coming in here, is equal to the rate of decay. And so that's called the state of equilibrium. That is, the number being produced, the number being changed back into nitrogen atoms, number of nitrogen atoms converting into carbon-14 and the number converting back, disintegrating back, are equal. So we have an equilibrium state. The amount produced equals the amount decaying back or disintegrating back. So it's stable. That's the assumption. But the radio calibration, they had in the calibration curve, they go back to this time here, and this is their calibration curve. The problem with it was he made that assumption based upon the fact that he assumed the atmosphere was billions of years old, which, of course, according to atheist models, it has to be that old. Of course, or atheism demands it to be that old. But he assumed it was that old, and lo and behold, that should have brought it to equilibrium. Now, let me illustrate this. If you started putting water into a tall storage tank, several hundred feet high, and had a hole in the bottom of that tank, a certain size pipe coming out of it, if you had the water flowing in at a certain rate, and then it flowed out of the small hole toward the bottom. As the water level got higher, the pressure would become bigger. Now, if you've ever gone down and swim deep into under the water, you can feel the pressure on your body. The pressure goes up as you go down. And I've tried to dive down several feet down in the past, and you can feel the pressure on your body as you go deeper and deeper. But it's very simple physics. It's simple physics. High school physics would learn this. So what would happen is this tank gets fuller and fuller. The flow of the water coming out of it would be faster due to the high increased pressure. And at some point, if the tank was deep enough, the flow rate coming into it would equal the flow rate coming out that orifice at the bottom of the tank, if you made the tank deep enough and had a constant flow coming in. If you made it deeper and deeper, at some point it would reach equilibrium. That makes perfectly good sense. That's a good illustration, in my judgment, of what would happen. What comes in goes out. Same thing happens with our oceans. The water that flows into the ocean evaporates and comes back out and recycles. So we have that occurring. So the oceans don't get full. In fact, the Bible even tells us this, but everybody can see that in their if they have any sense about them at all. Now, right here is the radioactive radiocarbon scale in time. And so it decays in a logarithmic base E, or Naperian logarithms, natural logarithm form equation. That's all of nature that I've ever seen decays that way, with that form, that mathematical relationship. And what happens, if you notice down here, this is tending to level off down here. And it's getting down to where it doesn't change very much at all. And that's what we're seeing here. So that's being produced, it eventually decays downward in time. And about 28,650 years, it's pretty well stable. It's gone down to almost nothing. So after about 50,000 years, the radiocarbon should have, almost all of it should have decayed down to zero, or virtually zero, not exactly zero, but very, very, very small amounts of it should exist after 50,000 years. Now, here's a problem that they run into whenever they do this and look at it. They found radiocarbon was produced by atomic bombs that were tested back in the 1960s. And a lot of them were tested back in that time by both the Russians and the United States. And France and England also tested them as well during that time. And this blue line assumes equilibrium. That's the assumption. This is the amount of radiocarbon. They quit testing them so much, and so the radiocarbon has been decaying downward. Notice it's come down pretty good after this spike around 1963. And so this is Wellington, New Zealand, and the Southern Hemisphere. The Northern Hemisphere, there's probably more tests than in the Southern, but hydrogen bombs were also tested this time as well. The radiocarbon in the bomb spike occurred about 1965 or somewhere thereabouts. Right? Probably just enough to increase our cancer rates over here about 20 years later and all over the world. Yeah. But I'll get off that, not worry about that. Willard Libby is a picture of him. He was born in 1908, died in 1980. He came up with radiocarbon dating techniques. He's the one that invented it and got a Nobel Prize for it, and for coming up with this system. Here's some more information about it, about radiocarbon equilibrium. Keep in mind now, they assume it's at equilibrium. Libby did not get the half-life correct, and they ignore this with all of his calculations. They just ignore it, but he didn't get it correct. The amount of radiocarbon in the atmosphere has not been constant. He assumed it was. So he got the half-life incorrect, even with their methods of coming up with it now. And he had the assumption that there was a radiocarbon was at equilibrium, and it wasn't. These two problems dealt with by a calibration curve, so they have a calibration curve to correct for it. I call this a fudge factor, basically, recalibrated for it. The samples might be contaminated. So that they take this fossil that's been buried, that is, let's say an animal or a plant, and they use this radiocarbon on living organisms only, such as plants or animals remains or human remains. They would look at this, but if it's buried in the ground, how do we know the water didn't seep down and bring radiocarbon into it or take it out of it? We just don't know. Samples might therefore be contaminated. Different reservoirs, oceans have different amounts of radiocarbon. We're going to show this. I'm going to give more information to show this. Annual fluctuation in the production of radiocarbon makes dating annual plants problematic. Now, think about it this way. The Earth's tilted on its axis. You're going to get more or less of these solar particles, that is, neutrons or protons. Neutrons or protons coming in to produce radiocarbon. I'll get more or less of them at different times as the Earth is tilted toward the sun or away from the sun at different parts of the Earth. Trees tend to have radiocarbon levels when taken on the average that are more stable. They live a long time, so they tend to be more stable than the short-lived plants that are annual plants, for example. Here's their equation. This is your basic form of a half-life equation. N sub T is equal to N sub O. N sub O is the N sub T over here. The number of the isotopes, number of the particles at time T equals N sub O, the number at beginning of when this was formed. If it's in a tree, it's when the tree first was formed, or when an animal lived or a human lived or something lived. And we're talking about radiocarbon, of course. base for natural log of 2.71828, and it goes on. That's a good approximation of it. Minus lambda is your decay rate, and T is your time. And so we have, they can measure in sub T, they know E, and they claim to know the lambda, the decay rate. Let's assume they know it. And so they can calculate the time then, but they got to assume how much they had at the beginning of the daughter isotope. That's their problem. Got to make an assumption about it. And they use T to calculate, that was directly solved for T. But they assume they know the decay rate. They assume they got a good measurement over it. I will admit they probably have good accurate measurements of this quantity, but they have to assume N sub O, that's an assumption. And they don't have the decay rate right. They didn't have the decay rate right for radiocarbon at the beginning. And they assume there's nothing that could change that decay rate. So there's several assumptions here, and this most critical assumption is they assume N sub O. Now, let's go back. And this is quantity remaining after time T, and N sub O is initial quantity. Decay constant of the substance, time after the beginning of the decay process. Oh, there are 4 variables in this equation. They only know 2 of them. They have to know 3 of them to solve for the 4th one. They have to assume N sub O. They don't know it. And they don't know it by scientific method. They don't know it by observation, particularly if we go back 20,000 years or 10,000 years or whatever time they want to go back. Again, no one was there to observe it, to actually measure. Now, we're going to stop here with this, and next week, Lord willing, this will be a convenient time to stop. We're going to look at the initial quantity of radiocarbon is not known with any certainty. What we're going to show is, in this next section, the next study, that will demonstrate that there are many instances that the initial quantity of radiocarbon is not known, and we can prove it. And we'll show it. And we'll show it with a number of different places in the world, a number of different organisms, and we'll show why it's different. And this shoots the whole system down. But I will tell you this, if you go back and assume equilibrium occurs, equilibrium should occur in less than 100,000 years. Something more like 50,000 years. You should have equilibrium. But if the atmosphere is not at equilibrium, that proves that the atmosphere is less than 100,000, or actually less than 50,000 years old, based upon when an equilibrium should occur. We do not have equilibrium. If you assume uniformitarian assumptions, we're going to show this later, but that actually shoots down the old Earth theory. Radiocarbon is not at equilibrium. Now, we're going to stop here with this, and are there any questions or comments before we stop?